Okay, hello everyone. I remain your tutor, Mr. Life Changer. In this video, I'm going to be continuing on the heat capacity series, heat and heat capacity series. So this is the second video. Okay, so here we see method of mixtures. The number 11 question says 200 grams of water at 80 degrees Celsius is mixed with 300 grams of water at 200 degrees Celsius. What is the final temperature of the mixture? Now, in a method of mixtures, when you mix two different substances of two different temperature, there is definitely going to be heat transfer. Heat always transfer from the hotter body to the lower body. And according to the method of mixture, the heat gained by the colder body is going to be equal to the heat loss by the hotter body, because the hotter body is going to lose heat, but the colder body is going to gain heat. So the formula is simply heat gain. Heat gain is equal to heat loss. I want you to note that, okay? But the same formula, still mc theta and still mc theta. But I like to say this here, that here we are going to write it as mass of the colder body. Let me say m1c1. Then this is going to be theta 1 minus theta m. Now this theta m here represents the temperature of the mixture, because after mixing them, the both of them will end up having a common temperature. That's the temperature of the mixture. So theta 1, oh sorry, this should be heat. Let me correct this, please. Okay, because heat gain means it is the colder body, so it's supposed to be temperature of mixture minus the temperature of the colder body. Okay, because the colder body is going to have a lower temperature than the temperature of the mixture. Okay, but in the case of this, it's going to be m2c2. Then the temperature here will be theta 2 minus theta m. That means minus the temperature of the mixture. Don't forget that. So the hotter body will definitely be higher. Remember, it's just like when you mix a substance, let's say water of 80 degrees Celsius to another water, and that one is 20 degrees Celsius. When you mix them, you are going to have a normal temperature, but that normal temperature is going to be less than the temperature of the hot water, and it's going to be higher than the temperature of the cold water. So many times here we can be asked to find temperature of mixture. So if you use this formula, you would not have any problem with this at all. Now it says 200 grams of water at 80 degrees Celsius is mixed. So the first mass here is 200 grams, which is 0.2 kilograms. I have to convert since the specific capacity has kilogram. Then the initial temperature of this guy here is 80 degrees Celsius, and it is mixed with 300 grams of water. The second water is 300 grams, and the temperature of that one is 20 degrees Celsius. What is the final temperature of the mixture? The final temperature of the mixture is theta m. Okay, all you need to establish first of all is which one is the colder body, which one is the hotter body. Of course, this is the hotter because it is 80 degrees Celsius. This is the colder, it is lower in temperature, 20 degrees Celsius. So the heat loss by the hotter body is going to be equal to the heat gain by the colder body. And we are going to maintain the formula m1c1. Then theta, it should be theta 1 minus theta m. Okay, the hotter body minus the temperature of the mixture equal to m2c2, but this one now will be the temperature of mixture minus the colder body. Please don't forget this. Kindly note this, okay? So now, but I want to say something here, that both of them are water, so their specific heat capacities, I don't need to write them. It will definitely cancel each other. It is given here 4200, but it's not necessary. It's the same on both sides, 4200. So if you can divide both sides, you're going to get that value. Now substituting the values, now here the mass is 0.2, and the temperature in theta 1 is 80 minus the temperature of mixture, then equal to, here m2 is 0.3, okay, times, okay, this is 0.3 kilograms, okay, times theta, temperature of mixture minus theta 2, theta 2 is 20 here. So if we open this bracket, 0.2 times this is going to give us 16 minus 0.2 theta m is equal to this times this is 0.3 theta m minus this times this is 6. Okay, so if we cross not crossing multiply, taking like terms, 6 coming here, this going there, you're going to have 16 plus 6 is equal to 0.3 theta plus 0.2 theta. If this crosses, it becomes plus 0.2 theta. If minus 6 crosses, it becomes plus 6. So 16 plus 6 here is 22 equals to 0.3 theta plus 0.2 theta is 0.5 theta. So you're going to have theta now to be equal to 22 divided by 0.5, which is 44 degrees Celsius. That's the temperature of mixture. Very, very interesting. Very life-changing. Very interesting. Okay. Now that leads us to the second one. It says a 0.5 kilogram metal block at 100 degrees Celsius is dropped into 0.2 kilogram of water at 20 degrees Celsius. The final temperature is 40 degrees Celsius. What is the specific heat capacity of the metal? Now this is very simple, very, very easy. Still the same thing. The mass of the metal, I can call it M1, is 0.5 kilogram, and the initial temperature is 100 degrees Celsius, and obviously the hotter one, and we are looking for the specific heat capacity. We don't know what it is, but the mass of water M2 is 0.2 kilogram, and the temperature of water here is 20 degrees Celsius. Then the specific heat capacity of water is given to be 4,200. Okay, 4,200 joules per kilogram per Kelvin. Okay, so remember the formula, M1 C1. Then here is going to be theta 1 minus theta m. I'm going to subtract this from the higher, this is the higher temperature. So it's equal to M2C2, and this one I can say temperature of mixture minus the lower temperature. It doesn't matter which one I put as my theta 1 or theta 2. What matters is that you should know that the higher temperature should be minus the temperature of mixture, and the lower temperature should be subtracted from the temperature of mixture. That's all you need to know. I hope that makes sense. So this is now your M1 here is 0.5. Your C1 is the capacity of let's see, this is what we are looking for, the specific heat capacity of the metal. Then the theta 1 is 100 minus theta m. The temperature of mixture should be given here. Okay, it says the final temperature is 40 degrees Celsius. Can you see that? That's the temperature of the mixture. So I'm going to write here to be 40. Now equal to M2 is 0.2. Specific capacity of water is 4,200. The temperature change, the temperature of mixture is 40. The temperature of water there is 20. You see? So this is going to be 0.5 C1 into 100 minus this is 60. Equal to this times this is going to give us 840 times 40 minus 20 is simply 20. Okay, that's very, very important. So now this is going to be, this times this is 30, so 30 C1 is going to be equal to, this times this is 16800. So C1 is going to be 16800 divided by 30. So that is going to be 3 in 16, I think that is 5. Then in 18, 3 in 18 is 6. So this is 560. So it's supposed to be 560 joules per kilogram per Kelvin. There is no 560 here, and I don't think I made any mistake here. There is no mistake here. Yeah, no mistake. So the answer is 560. The option is not here. This is wrong. So 560 joules per kilogram per Kelvin. Now that leads us to the next one, number 13. It says 150 grams of a metal at 90 degrees Celsius is placed in 100 grams of water at 25 degrees Celsius in a calorimeter of heat capacity this. I wanted to mention this. So the final temperature is this. The specific heat capacity of the metal is, now I want to say this, that In the first two cases that we solved, the first earlier cases that we solved, there was no calorimeter. Calorimeter is a vessel where all these mixtures take place. Now, if the specific heat capacity of the calorimeter is not given, then you can ignore it. You can forget about it. Are you with me? But if it is given, then you cannot ignore it. You have to include it in the formula. So I'm going to rewrite this formula now. We have heat loss is equal to heat gain. Okay, it is a hot substance that loss. So I'm going to say M1C1 theta 1 minus theta m is equal to M2C2 theta m minus theta 2. Now, but plus, that means heat gained by the water plus the heat gained by the calorimeter, because the container, the calorimeter contained water earlier. Now you are going to add that of the calorimeter, which is going to be M3 C3 then theta m minus theta 2. Now the change in temperature, this is for the water or the content, and why this is for the calorimeter. Now you should note that the temperature change in the calorimeter is the same as the temperature change in water. They have the same temperature change. I hope that makes sense. Okay, then you have this one. So here the mass of the metal, I can convert this to 0.15. That's the mass of the metal. The specific heat capacity of the metal is what we are looking for. They say find the specific heat capacity of the metal, so I'm going to write it as C1. The temperature change of the metal, the initial temperature of the metal is 90, then minus the temperature of mixture, the final temperature, see it here, the final temperature is 35, so the temperature of mixture is 35, equal to the mass of water. They said 100 grams of water, which is 0.1 kilograms, times specific heat capacity of water, we already know that that's 4,200, times the temperature change of water, which is the temperature of mixture, which is 35, minus the temperature of water, which is 20. Can you see that? That is for water. Then plus the calorimeter. We are not given the mass of the calorimeter. We are not given the specific heat capacity of the calorimeter, but we are given the heat capacity. And I have mentioned this in the previous video, that heat capacity is equal to mass times the specific heat capacity. Heat capacity is mass times the specific heat capacity. Don't miss that. Okay, so that means the mass here is mass times specific capacity is the heat capacity, which is 20. So I'm going to replace MC with this 20. That's heat capacity. MC means heat capacity. Don't forget that. Then the temperature change will be the same thing as that of its content, which is 35 minus 20. This is interesting. This is interesting. So let's solve this now. This is going to be 0.15 C1 times 90 minus this is 55. Okay, equal to this is going to be 420 times this is 15. Then plus this is 20 times 15. Okay, so this is going to be 0.15 times 55 C1. I don't have a calculator here. This is going to be 600 plus this is 6,000 plus 300. That means 6,300. Then plus this is going to be 300, I guess. Yeah. So this is going to be 0.15 times 55 C1 is equal to this plus this is 6,600. So C1 is going to be 6,600 divided by 0.15 times 55. Well, I think 11 can go already. 11 here 5, 11 here 6, 600. And I think 5 can go, 5 here 1, 5 here, this should be 15, that's 150, right? I hope that is correct. 5 times this 120, sorry, 120. So this is going to be 120 divided by 0.15. You can use your calculator, you know, to get this. I don't have a calculator here, so let's divide by 15. This divide by, okay, let's say 3 here 5, 3 here 4. So 5 can go in this to be 800. So the answer is 800 joules per kilogram per Kelvin. And the answer is not in this option. Maybe when you use your calculator you could get something different, but from what I have here, this is our answer. and I think our answer is correct. I don't think I made any mistake here. 3s5 3f4 yeah. So the answer is 800 joules per kilogram per Kelvin, which is not in the option. Okay, what is most important is that you know how to solve this. Now this one says this one says that a 0.2 kilogram brass block, and they give you the specific capacity, at 120 degrees Celsius is dropped into 0.3 kilogram of water at 20 degrees Celsius. What is the final equilibrium temperature? Here we are not given any calorimeter, we are not given any vessel, so we are going to neglect that. So it's definitely going to be M1C1 theta 1 minus theta m is equal to M2C2 theta m minus theta 1. So the initial mass, the mass of the block is 0.2. The specific heat capacity of the block is 380. Okay, then the temperature change, the block was 120. The temperature of mixture, the final temperature is what we are looking for. Then equal to M2, water is 0.3. Specific heat capacity of the water is 4200. Then the temperature change, we are looking for the final temperature, then minus the initial temperature of water here is 20. So still the same thing. And this is going to give us 72 into 120 minus theta m. Okay, is going to be equal to, and this is going to give us 1260 into theta m minus 20. And I think this is going to give us 7200 plus 2 plus 440. Okay, this is going to give us 8640, I guess. Then minus this is 72 theta m equal to, this is 1260 theta m minus 20 times this is 25200. Okay, so if you collect like terms now, this is 8640 plus 25200 is equal to 1260 theta m plus 72 theta m. Okay, so this plus this should give us, maybe I should leave you to complete this. You can give me the answer in the comment section. Okay, that is for that one. Okay, so the next question here is not concerned, so I'm going to stop here and continue in my next video. Okay, I'm going to continue in my next video. This is not our concern here. So thank you very much. See you in my next video. Okay, yeah, so much. Bye bye for now.